Okay, so we have been studying optimal auction design for last one or two lectures. And so the main idea here is to use the characterization of DSIC direct mechanisms to come up with an optimal expected revenue maximizing auction for single objects. Okay, so that was the idea, and that's what we did last time. So let me just quickly recap how we did it. So we started with imposing very weak notions of incentive and participation constraint, which is Bayesian incentive compatibility and interim individual rationality. Okay, so these are the constraints that we put, and our objective is to maximize expected revenue. Okay, and so this is a very natural problem. Every seller, before deciding on a mechanism, wants to maximize its revenue, and often that means that he wants to maximize the expected revenue that he can get from the mechanism. Okay, so that's basically our objective function. The drawback of this approach is that because the seller wants to maximize expected revenue, he should have a good idea about the distribution of values. Then only he can compute an expected revenue. So this G function, the distribution function, should be known to the seller for this approach to work. Okay, so what we assume in this analysis is that G is independently distributed. So every agent draws its value independently. And we'll come in the next lecture, we'll also consider the case where the values are correlated and what happens in that case. But for Meyerson's analysis, we assume that values are independently distributed. They need not be identical, so bias might be very asymmetric, but at least they are independently distributed.
So the BIC characterization only works for independent distributed types, right?
That is also true. So the characterization that we have also works for independent distributions. Yeah. Okay.
Sir, only for independent distribution, right?
Only for independent distributions. Yeah.
Oh, okay.
So we set it up as follows. So we want to maximize expected revenue subject to BIC and IIR constraint. And the expression for that expected revenue is that. And so we have this problem. So what we do is basically use this characterization from the earlier lectures of BIC and IIR mechanisms, which says that every such mechanism must satisfy that F is non-decreasing in expectation, and the expected payment formula satisfies this property, and the lowest type's expected payment is less than equal to 0. So if these three conditions are true, then it's if and only if the mechanism is BIC and IIR. So we use this to simplify the expected revenue expression. And so by doing some nifty, order of integration manipulations and so on, we come up with a simpler expressions for this expected revenue, which involves, two terms. One is this sum of expected revenue at the lowest type. And the second term is just like, expected virtual value. Okay, so why is it expected virtual value? Well, virtual value is this, and it so happens that if we allocated efficiently, that is, we always allocated um, to the highest valued agent, then then the expected surplus from the mechanism is expected value, right? Because that's basically the expected value realized by all the agents. But we are not, the revenue term would be smaller than that, because That's the maximum that you could achieve, which is the expected efficient value. So the revenue term is smaller than this. So this is kind of the information rent paid by the seller, right? So basically, if the seller knew everybody's value, then he would just at every type profile approach the buyer with the highest value and make him a take it or leave it offer. In that sense, he would take away all the surplus at every type profile. So the expected revenue is just the expected highest value. Okay, but in this case, he has to pay some rent to the buyers, because now each buyer has some private information, and to make these buyers truly reveal those private information, uh, this is kind of the expected revenue term, is subtracted from this TI, right? So that's basically what is happening. And so this, uh, this private information on the part of the buyers is making the seller give them something and keep the remaining. Okay, so that's basically, uh,
Also, na,
yeah.
a virtual could be a negative also.
Virtual could be negative also, but I'm just saying that this TI minus this is kind of a way of paying this particular each of the buyers something. Okay, and so that could be negative. So that means that he may, an interpretation is like, uh, well, in the optimal auction, if it turns out to be negative, we have this option of not allocating to that buyer. So in that case, we won't allocate it to him. But whenever we allocate, we see that we are kind of maximizing the virtual value. So we are giving some rent to those allocated buyers, basically. And so what we see is, once you formulate it like that, revenue maximization is same as expected virtual value maximization, then the problem becomes very simple. It's simple because we have got rid of all the P terms from the objective function. So it's a problem in F, and hence we can forget about constraints on P, because remember, the constraint on a set was this is BIC and IIR, and we know that that is equivalent to F being non-decreasing in expectation in this term. But now the objective function only has F. So if you just impose the F constraint, which is non-decreasing in expectation, payments can always be determined automatically. How can payments be determined? Well, uh, fix a non-decreasing. So whatever uh, the outcome of this optimization exercise, once we get an F which is non-decreasing in expectation, we can always construct a P such that the revenue equivalence formula holds. Okay, and pi I 0 can be set equal to 0. Okay, because this is, remember, to construct P, all we need to ensure that pi I Ti satisfies is equal to this, but this is determined completely by F. So for any F, we can pretty much determine uniquely almost, I mean, subject to this, the small disclaimer that this is only an expectation, but there are many ways to compute payment so that this is satisfied from an F. Okay, so that's the main observation, that once we find an optimal solution to this, P can always be determined so that the revenue equivalence formula holds and pi I 0 equal to 0. Okay, and we'll see how we do that for the optimal mechanism that we design, essentially. Okay, so what happens is, basically the problem which involved F and P is now an optimization problem only in F. Okay, and the expected virtual valuation needs to be maximized subject to the constraint that f is non-decreasing in expectation. Okay, so that's what this theorem was about. And the solution is kind of a bang solution, which basically says that look at every type profile, and basically if everybody has negative virtual value, then basically this expression is maximized by putting all the fi's equal to 0. If a single agent has non-negative virtual value, then set FIT equal to 1 for the agent who has the highest virtual value. Okay, that's how you can point-wise maximize it. This does not ensure that this NDE constraint is satisfied. But what we showed is that the NDE constraint can be satisfied if the virtual value function is non-decreasing. Okay, and one way to make that non-decreasing is to assume that the hazard rate is non-decreasing. Okay, and that basically what we call a regular distribution. So any distribution GI is regular if the virtual valuation function is strictly increasing. Okay, and under that, the unconstrained optimal also satisfies the non-decreasing in expectation constraint. In fact, it satisfies the stronger constraint, stronger condition that the allocation rule is non-decreasing. Not only is it non-decreasing in expectation, but also it is non-decreasing. That is, for every t minus I, the allocation rule is non-decreasing in agent I's type. So that's a stronger property, and basically what that allows us to do is to derive what the optimal allocation rule is, which is that under regularity, we have this rule that highest non-negative virtual valuation guy wins, and the payments can be determined as follows. Because the allocation rule is non-decreasing and it is deterministic, we know that this allocation rule can be implemented by a DSIC mechanism. And that DSIC mechanism also, we know how it will look because it is deterministic. It has to be a cutoff type payment where losers must pay 0 and winners pays the least type at which she starts winning. Okay, such a payment rule will make this allocation rule a DSIC mechanism. Hence, the BIC constraints that we had imposed at the beginning will also be satisfied. Okay, so basically that's what we do. So once we determine this allocation rule to be optimal, we realize that this optimal allocation rule is actually non-decreasing, and hence we can devise a payment rule which will make it a DSIC mechanism, and we do exactly that. So every agent has a reserve price WI inverse 0. So that's the point at which this agent starts having non-negative virtual value. And if your value is less than this reserve price, you don't participate. All the participating agents, we look at them and choose the one who has the highest non-negative virtual value. And so winner makes this cutoff payment, so which is the infimum type needed to report so that virtual valuation becomes non-negative and exceeds the second highest virtual value. Okay, so,
Here,
yeah, go ahead.
the virtual value, is it only relevant to the seller or is it relevant to the agent?
So it's part of the allocation rules. So basically, the when the seller is specifying the mechanism, it has to specify it using the virtual values. Okay, so it will say that. Of course, we are talking about the direct revelation mechanism. I'm going to come to indirect implementations in a bit, but in a direct revelation mechanism, the way it will work is, the designer will say, everyone report your value to me. and here is what I will do to your values. I will construct from your value this new thing called the virtual value. And if the virtual values are non-negative, then I will consider your values. Otherwise, you are not considered. Okay. Once I take the set of bidders who are considered, I will choose the bidder as the winner who has the highest virtual value. That's how he will use it. So it's, I guess it's relevant for both the seller and buyer because, you know, it's specified in the mechanism.
So are we
Yeah, go ahead, Anirudh, finish it.
are we sure that it is non-manipulable, since it might so happen that my value is high,
Yeah.
but still my virtual value is lower, and so the object is actually allocated to someone else.
Yeah. So by our characterization theorem, this is a non-manipulable mechanism. It's a DSIC mechanism. And the reason is simple because the allocation rule is non-decreasing and the payments being chosen are this cutoff time. And we know that those are DSIC mechanisms. Right? So,
But the payments are low my type.
the payments are?
Then
Uh, sorry, I could not hear you.
Yeah, I was saying that the payments are lower than the types.
Yeah, that's okay. So that's okay. So how can I manipulate, for instance, suppose, uh, you know, I'm the winner, right? Okay. So can I manipulate and get better payoff? Well,
No.
because as long as I'm winning, I pay the same amount. So I can't manipulate my payment if I'm winning. I get zero payoff if I don't win, so it's not a manipulation. Can I manipulate if I lose? Well, if I lose, I get zero payoff. Can I get positive payoff by manipulating and winning? Well, not really, because if I win, my payment will be the what? My well, uh, which will be the um, so
Okay. The
so
virtual value.
it will have to be the second highest. I mean, it's going to be complicated to describe, but it's going to be the least value required for me to beat the second or the highest virtual value now, and so on. And so you can show that that will always be negative payoff. Okay.
Yeah.
Yeah. So it's all coming from our characterizations and so on. So as long as I have a non-decreasing allocation rule, and if I define the payments like we have defined, it will always be DSI. And it will satisfy ex post IR also. Yeah, somebody else had a question? Okay, maybe not. Okay, so what I'm going to discuss today is basically two things. First is, I'm going to focus exclusive on the symmetric agents case, and I'll basically give you some intuition about why the optimal auction in this case involves a reserve price. Why is it optimal to not sell the object at some places? Okay, so that's one thing that I'm going to do. The second thing is to basically think of alternate implementations, like um, is Vickrey auction the only way to achieve an optimal auction? Okay, are there other ways to? Are there other optimal options? Okay, so of course, I'll show that there are other optimal options, but these mechanisms are kind of indirect mechanisms, but they all have the same direct revelation mechanism. Okay, so So you should always keep this in mind. And I hope it will become clearer. So let me stop the video so that the quality of transmission is better. Okay. So let's recall what is the symmetric case. So in the symmetric case, all the agents type spaces are the same. So it's some 0 to B, and this B is same for everyone. And all the GIs are the same. So the distribution using which agents derive, draw their values is the same. Okay. So as a result, the virtual value function is the same. Okay. So remember, this is the virtual value function, and this depended on G subscript I. But now if the G's are the same, then everybody has the same virtual value function. So instead of WI, we are just going to have W here. And of course, because at any type profile, different agents have different types. So the virtual values may be different at a type profile, but the functions are the same for all the agents. Okay. So one advantage of that is that because the function is the same, basically under regularity, highest value agent is also the highest virtual valuation agent. Okay. So basically, if two agents have values of 5 and 10, then the virtual value of 10 agent is larger than the virtual value of 5. Okay, that's because of regularity, right? Because this virtual value function is monotone under strictly increasing under regularity. So that's an advantage. The other thing is everybody's reserve price becomes the same. Remember, this was the reserve price for each of the agents, and this was each agent has a different reserve price in the asymmetric model. But in the symmetric case, because the WIs are the same, this just becomes W inverse 0, which is same for everyone. Okay. So the allocation rule and the payment rules become now very easy. So the seller basically allowances this reserve price W inverse 0, and whoever has value above this reserve price, it chooses the agent with the highest value amongst them. Okay, because the highest valued agent is also the highest virtual value. Okay, and the payment is basically the loser, of course, pays 0, but the winner pays the least type at which she starts winning. But what is the least type at which she starts winning? Well, first, her type has to be above W inverse 0, reserve price. Also, it has to beat the highest amongst the other types, which is the second highest type. So that's the infimum type at which she wins. So the payment will be max of the reserve price and the second highest value. Okay. So that's what we call a Vickrey auction with a reserve price W inverse 0. Okay. So basically, highest bidder wins and pays an amount equal to maximum of reserve price and the second highest type. So at least in the symmetric case, the description of the optimal mechanism is simple in this sense. So we did this example of the asymmetric case. Now I'm going to do an example with a symmetric case. Okay. So here I have two agents whose types are drawn uniformly from 0 to 10. Okay. So the virtual value function for both the agents is the same, and that will come out to be Ti minus 10 minus Ti. Okay. So because of uniform, so that's 2 Ti minus 10. So the common reserve price is 5. Okay. And we know that agent with higher virtual value is also agent with higher value. So the allocation is highest value agent if value not less than 5. Otherwise, do not allocate the object. Okay. And payment is loser pays 0 and winner is higher of 5 and second highest value. So higher of the reserve price and the second highest value. Any question on this? Example. Okay, so this is, if I were to draw a diagram of what happens at every type profile, this is how it looks. So basically, this is the entire type profile space, 0 to 10. So there are these reserve prices of 5 and 5. Okay, and below the 5, 5, nobody wins. So this blue region, the object is not allocated. In the yellow region, agent 1's value is higher, so agent 1 wins. In the pink region, basically agent 2 has a higher value, so she wins. Okay. So at this point, let me pause and ask you, like, let's look at the region where agent 1 wins. Where does agent 1 pay, make a payment equal to its reserve price? I mean, equal to the reserve price 5. What is the region? Can you tell me roughly? Where will agent 1 pay 5?
As long as 2 is less than 5.
As long as T2 is less than equal to 5, right? Because if T2 is less than equal to 5, remember in this particular box below, agent 2 is no longer qualified. Okay, so the minimum type, at which agent 1 starts winning is the reserve price, which is equal to 5 in that case. Okay, right? So in this box below, agent 1 makes a payment equal to 5. Okay, above this box, in this triangle, agent 1 makes a payment equal to the second highest value. Okay, and here in for agent 2 also symmetrically, in this box, she makes a payment equal to 5, and in this triangle, she makes a payment equal to agent 1's value. Okay.
I have a question.
Yeah.
In this setting, we will always get a reservation price.
Auction recommends a reserve price of 5 in this case. So the object is not allocated in this region.
So what we are saying is, if seller wants to maximize its revenue, it will have to consider Vickrey auction with reserve price.
Yes.
But earlier we considered many cases where there was Vickrey auction without any reserve price.
Yeah.
So it means those were not seller revenue maximizing
That's
mechanisms.
correct. That's correct. Okay. So in fact, your question is very good, because my next slide is about that. Okay. So so basically, the overall concern is, how does a reserve price boost revenue? Okay, because we saw that, this is like 1/4 of this type profile space. So basically, because everything is uniformly distributed, 1/4 of the time we will not sell the object, essentially, right? So if I as a seller is looking at this mechanism, I know that 1/4 of the time I will not sell the object. Okay, then basically the question is, how can that be an optimal mechanism? Okay, so basically what the seller could have done is not set a reserve price. So it could have just conducted a Vickrey auction. Okay, so what we see is there are two opposite effects on revenue by not setting a reserve price. Okay, so I'll tell you what. So of course, in the unassigned area, this particular area, now the seller will sell the object because there is no reserve price. And in this area, basically she will collect revenue which is equal to the second highest value. expected second highest value in this region. That's the boost in revenue that she will get, because now there is no reserve price, so she will collect expected second highest value in this region as the revenue. But there is also a down effect, which is that revenue in some other areas will go down. Okay, so which areas will the revenue go down? Let me show another picture that might be better. Yeah, let me try to share. Oh, never mind. It's okay. One sec. Can you all see the new picture?
Yes, sir.
Yes, sir.
Okay, so this is the same thing that I was talking about earlier. So now, if we do a simple Vickrey auction, then look at this square, bottom square. Remember?
Okay, yeah. So here they will pay something less than 5. That is that
Yeah.
what you're saying?
Right. So earlier we argued that in this region, agent 1 used to pay 5, right? But now he won't pay 5 anymore, because there is no reserve price. So he'll pay the second highest value in this region. So earlier we were guaranteed to get 5 at every type in this region, at every type profile in this region. Similarly, we were guaranteed 5 at every type profile in this region. But now in this region and this region also, we will get expected second highest value. So we're going to lose out revenues in two regions, two of these squares, and gain revenue in one of these squares. Here the revenue will be unaffected, because both with reserve price and without reserve price, they were paying the same. Okay, so we lose out in two places and we win in one places. So the effect is that in expectation we lose out. Okay.
Sir, precisely due to which condition the losing out area is more than gaining area?
Because here here the winner always pays 5, right? If you have reserve price.
Which of the conditions ensures that the losing area is always greater than winning area?
Is it because we have taken a symmetric case? So, for example, if one person had a very high reserve value, so do you think it is possible that in expectation we might actually gain by not keeping a reserve price at all?
Okay, so let me first say why, at least in this example, we are gaining overall. In this example, we are gaining overall because the overall gain in these squares, okay, in each of these squares is the same as the overall loss in these squares. And because of uniform distribution, the total expectation of these two areas is exactly double the expectation from this. Okay, so in fact the difference will be exactly the expected revenue of this area plus expected revenue in this area minus this, which will be one of these two will cancel, and you will just be left with the expected revenue from one of the squares. That's the additional gain you will have, and that is purely from uniform. If I did not have uniform, then these this reserve price will be adjusted accordingly, so that so that any kind of adjustment will lead to a lower revenue, essentially. If you did not have a symmetric case also, the individual reserve prices are calculated so that any such adjustment to the reserve price will lead to a lowering of revenue.
Okay, yeah, I see.
Okay, so here, of course, I'm taking the extreme case where I'm putting the reserve price to 0. You can also do a local argument where say that suppose I had a reserve price of 5 minus epsilon. So why does that lead to a lowering of revenue? Okay. So somehow this 5 is kind of a global optimum for a reserve price.
Reserve price. Okay.
So doesn't this directly follow from maximization process?
Yeah, it follows from maximization process, but I'm just telling you that trying to give you a roundabout explanation of why we ended up having a reserve price and not have any reserve price. Because if you tell it to someone and say that 1/4 of the time we won't win we won't allocate the object, he or she may say that, well, that's not good because we may be losing out revenue. But then you should, the counter to that is, in the process of allocating the object at those 1/4 of the region, you will have to allocate in other places using lower payments. Okay, so the payments in other areas will become lower. So the advantage of setting a reserve price is that the payments in other regions also gets boosted and the overall expected revenue goes up. Okay. So that's basically the explanation of why a reserve price is required. Okay, so basically it's important to have a reserve price because it boosts revenue in many areas, even though it may not assign the object in some areas. So optimal mechanism basically chooses a reserve price which trades off these losses and gains. Okay, so that's how the optimization exercise, implicitly does that for you.
Sir, in terms of social welfare, is it the optimum mechanism?
Definitely not, right? Because we, the social welfare means that we want to give as much as profit or payoff to the buyers. This is exactly the opposite. Here, the seller is trying to take as much as possible. So the expected payoff maximization of the buyers will require a different mechanism. So we discuss some of those mechanisms in those Green-Lafaux mechanisms and so on, remember. But a precise characterization of what that optimal buyer payoff maximizing mechanism may look like is basically difficult. Okay.
But sir, if we are trying to maximize the social welfare,
Yeah.
Payments should not matter, isn't it?
Well, payments matter to give incentives. So,
Yeah.
you need to have right payments to maintain incentive compatibility. So, for instance, if you just say that whoever has the highest value, I will give that object to that agent for free, you may think that that will maximize social welfare because you will give it to the highest valued agent and not charge anything. But that's not going to work because people will manipulate in that.
Yeah.
So you need to be, so payments will be required, and the point is to design the payments. So that's basically the constraint. So you need to have incentive compatibility and IR constraint and maximize the expected payoff of the agents. So the objective function will now look like, instead of maximizing expected revenue, you need to have this like maximizing the expected payoff of the agents. Okay, so UITI. Okay, so that will, yeah.
Can we say that the second price auction is social optimal?
Second price auction is definitely not social optimal, because we have seen that in the earlier lecture that something like the Green-Laffer mechanism does better than the second price, right? So remember the Green-Laffer mechanism, which said that I choose one of the agents uniformly at random and conduct a victory amongst the n-1 agents, and whatever revenue we generate from that, give it to this residual claimant. Okay, and if we choose this residual claimant with probability 1 over n, so that mechanism we showed in the last lecture generates more social welfare than victory auction. We showed that. If you
Yeah.
So victory auction will not do well because of the simple fact that at every type profile it generates some revenue. So the point of social welfare is you need to reduce revenue as much as possible. Okay, so the victory auction doesn't quite do that actually. In fact, that's a good point. That's a good point to look at this optimization exercise again. So we saw that here, this is the revenue maximization objective after all those manipulation. The objective function is just maximize highest virtual valuation, right? And the way we do it is, if the virtual values are negative, then set FIT equal to 0. Otherwise, set FIT equal to 1. Okay, for the guy who has the highest virtual value. Now, suppose as a planner, suppose the government says that you have to allocate the object at every type profile. So the constraint is that something like this blue area is not allowed. You cannot have the case that the object is not sold. So now you have an additional constraint in the optimization program. In FPs, BIC, FPs, IIR, and F, the sum of FIT is equal to 1 at every T. Okay, so there is an additional constraint. Okay, so what if you look at this objective function, now what will be the optimal mechanism?
Just give it to the highest one.
Just give it to the highest virtual value bidder.
Yeah.
Even if he has a negative virtual value.
Yeah.
Okay. So of course, with regularity, that rule is non-decreasing at all. But notice the following, that the highest virtual value bidder is not the highest valued bidder if agents are asymmetric, right? So I think we saw it in that example here also, that here, for instance, 7 and 8, this type profile, agent 7 has a higher virtual value than agent 2. I mean, agent 1 has a higher virtual value than agent 2. So even if you are forced to allocate the object at every type profile, you will not do a victory auction if the agents are asymmetric. Okay. If the agents are symmetric, then maximizing virtual value is same as maximizing value, because high virtual value is also the higher value under regularity. And so in that case, the optimal auction is the victory auction. Okay. So that is also a key point, that if you're forced to sell the object under symmetry, the optimal auction is victory auction with a reserve price of 0. That is a victory auction. But if the agents are asymmetric, it's an auction which chooses the highest virtual valued bidder, which need not be the highest valued bidder. Okay. So that's something to also keep in mind, and we'll come back to this point slightly later. Okay, so before I get to that point, so let me also, at least in the symmetric case, there are simple simple indirect implementation of this optimal mechanism. One, though, we know that victory auction is same as English auction, so you can always have this English auction implementation. So what's an English auction? English auction is an auction where the seller starts a price clock. Think of a continuous price clock at a low price, and that price clock continuously increases. Okay, and at any point, uh, every bidder, can stay in the auction, which means that the clock on the price on the clock is acceptable to the bidder. Whenever the price is too high, a bidder can drop out, and once he drops out, he cannot enter, basically. Okay, so you can show that if you start the price clock at W inverse 0, so which is the reserve price, and keep increasing, then basically the bidder who will win is the highest valued bidder who has value more than W inverse 0. And basically this is an English auction implementation of the Vickrey auction with that reserve price. Okay, so this is an indirect mechanism which does the same thing as the optimal mechanism. Of course, in the symmetric case. In the asymmetric case, this English auction implementation doesn't work, because now bidders have different reserve prices, and highest valued bidder is not the winner, and so on. So it won't work. But at least in the symmetric case, there's an English auction where the price clock starts at W inverse 0, and you can achieve the same outcome. Okay. Now, somebody asked me...
Sir, can we interpret English auction as a dynamic posted price mechanism?
Yeah, I mean, usually the posted price mechanism definition is like you announce a price, and whoever is interested at that price, you give to one of them uniformly at random. Okay, this is slightly, it's not, this will choose the right bidder essentially. Yeah. So there is also a first price implementation of the optimal mechanism. So for that, basically, you need to remember some properties of the first price auction that we studied in game theory 1. So in the case where bidders are symmetric, there is a symmetric equilibrium bidding strategy in first price auction with reserve price. And the exact formula of that bidding strategy is not important. But what is important is that that bidding strategy is strictly increasing. I mean, differentiable, of course, but we don't need to worry about that. But there is a strictly increasing bidding strategy which every bidder follows. And basically, an important aspect of that is that in equilibrium, higher valued bidder bids higher. So that means the winner is always the highest valued bidder. So at every type profile, the winner would be the bidder with the highest value. So what is the reserve price that we should choose in the first price auction such that it mimics the Vickrey auction outcome? Well, we know that we only want to allocate when the values of the bidders are, at least one of the values of the bidders is greater than W inverse 0. Okay, whenever the values of the bidders are less than W inverse 0, we don't want to allocate. Well, in that case, remember, a bidder with value W inverse 0 will bid beta W inverse 0. Right? Beta W inverse 0 is the bid of a bidder in first price auction when he has value W inverse 0. Right? We don't want bidders to participate in the auction if their value is less than W inverse 0. So that means that if we set a reserve price equal to, R equal to beta W inverse 0, then any bidder who has value less than that, would basically bid lower than the reserve price and basically will not participate. Okay, maybe I'm not clear, but you should just write this down and verify yourself that such a reserve price will exclude exactly the same set of bidders that we were excluding in the second price auction with reserve price W equals 0. Okay, so that's all that is required, because whenever bidders are winning, they're winning, the same guys are winning, and so the expectation, the expected revenue will remain the same as long as the allocation is the same. Okay, so there is a first price implementation of it. I mean, maybe in the slide it's not clear, but if you take this as an exercise and show that if you choose this as the reserve price, then the expected revenue is exactly the expected revenue in the optimal mechanism in the symmetry case. I think that's a good exercise for you to carry out in this. The exact form of beta does not matter. Don't need to worry about that. All that matters is in equilibrium, higher valued bidder bids higher, and basically the allocation rule is the same in both the cases because the exclusion level is the same. Okay, any questions? All right. So one thing, many people do not like here is that, Marston's analysis is heavily dependent on what priors are used. Okay. So, whether bidders are symmetric, asymmetric, the knowledge of priors is extremely crucial for deriving the optimal auction. Okay. But of course, it's an unfair criticism because without priors, even the problem is not well defined, right? What does the bidder, if a seller says that I want to maximize revenue, what does it mean? I mean, if it means that he wants to maximize exposed revenue, that means that every type profile he wants to get a mechanism which gives him the highest revenue. Well, that may not be possible because if you tell me a mechanism where it gives me the highest revenue at a given type profile, but it might be giving very bad revenue at other type profiles, right? So, like we saw in the example here, that the second price auction with a reserve price of 5 gives very good revenue in these regions. But if you set reserve price equal to 0, that mechanism gives very good revenue in the blue region. So it's not even clear that an exposed revenue optimal mechanism may exist, because every time you give me a mechanism, I can come up with another mechanism where the revenue in some parts is better, but revenue in some other parts is lower. Okay, in this simple time space, give me any mechanism, I'll construct another mechanism where revenue in some parts is better and in some other parts is worse. Okay, so it's not clear that we can actually maximize revenue in an exposed sense. So the most sensible thing to do here is to have an ex ante perspective of maximization. So we have a prior and we want to maximize ex ante revenue. Of course, the drawback of that is that to compute any ex ante term, we need priors, and so the optimal mechanism will be very prior heavy. Okay. So let me come back to my earlier point that if we are forced to allocate, like in many government cases, they will say that we want to maximize expected revenue, but we also never want to not allocate the object. Okay. So basically, at least in the symmetric case, we know that the optimal mechanism is the Vickrey auction. Okay. So you need to have a Vickrey auction with no reserve price in that case. In the asymmetric case, it's slightly complicated because you must allocate to the highest virtual value agent, even though he has a negative virtual value. But the highest virtual value agent need not be the highest valued agent. So this is also a key corollary of our exercise. So you should always remember this. But here is an interesting result, which was proved by Bulow and Klemperer. And the result is interesting. You'll see at the end of the slide why the result is interesting. So take a symmetric setting where there are n+1 agents. Okay, so there are n+1 agents. Each agent's value is drawn from the same support using the same distribution. Okay. Now, instead of doing an optimal auction for these n+1 agents, we know that if I do an optimal auction, it will be a Vickrey auction with a reserve price, and that reserve price requires prior information, because to compute the W inverse 0, I need what distribution this bidders are distributed. Okay. So suppose we don't like that. We have no information about the bidders distribution. So what we do is the following auction. We do a optimal auction with n agents, and basically whenever remember, optimal auction with n agents will also require bidders distribution. But let's forget that for a moment. Let's suppose that we could conduct an optimal auction with n agents. Okay, I'll come back to it. Why I am asking you to conduct an n agent optimal auction, but not telling you to do an n+1 agent optimal auction. So for the moment, think of this hypothetical setting that we conduct an optimal auction with n agents. But remember, optimal auction with n agents will sometimes not allocate the object. In that case, what we will do is, whenever we don't allocate, we give the object for free to the n+1st agent. Okay. So it's a suboptimal auction for the n+1 agents case, because if we had done the n+1 agent optimal auction, we would have set a reserve price and not allocated sometime. But here we are allocating always, and when we are allocating, so there are two places where we are allocating. One place is when we are doing an optimal auction with n agents and allocating there. If we cannot allocate within those n agents because of reserve price of the optimal n agent auction, we allocate to the n+1 agent for free. Okay. So this mechanism is BIC and interim individually rational and always allocates in the n+1 agent. From my previous slide, we know that the expected revenue of this mechanism is less than the Vickrey auction for n+1 agents. Remember, the optimal mechanism for n+1 agents, if you are forced to sell, is the Vickrey auction of n+1 agents. So the expected revenue of this mechanism is less than or equal to the expected revenue of Vickrey auction with n+1 agent. Okay, so this is the first important point. But now let's come back to this auction. Notice what is the expected revenue of this mechanism. Well, expected revenue of this mechanism is exactly the expected revenue of the n agent optimal mechanism. Because the only place where we are generating the where we are generating revenue in this mechanism is when we are doing the optimal auction with n agents. When we are giving to the n+1st agent, we are giving it for free. So the expected revenue of this mechanism is exactly equal to the expected revenue of the n agent mechanism. So what we have established is that Vickrey auction with n+1 agents generates more expected revenue than optimal mechanism with n agents. Is that clear? Any doubts in this? It's a very important and simple point. If you did not follow this argument anywhere, then you should seriously look at your notes when you go back. I can't hear you. Increase your sound. Not really, but try.
I'm saying, how did we choose the n plus one agent over here?
Choose any n plus 1th agent. Choose any one. Doesn't matter.
So he's common in this process. He's the same person.
It's common in this process. Yeah. So the mechanism is as follows. N plus 1 agents enter a room. I grab one of the agents and keep him aside. Okay. In the remaining n agents, I tell them to report their values. If their values are above the reserve price, I allocate, if at least one of the values is above the reserve price, I allocate to the highest valued agent and ask him to pay the highest of second highest value and the reserve price. If everybody has value less than the reserve price, I give the object to the agent I had taken out earlier for free.
So doesn't that sound like the like as if the n plus 1th agent was the seller only?
Not really, because no, not really, because if it was the seller, then it would be a different thing, right?
I mean, if the object is unallocated among the n agent setting, then we are saying that we are allocating it to the n plus 1th agent, like as if we are not allocating.
So the expected revenue of this mechanism will be exactly equal to the expected revenue of the n agent optimal mechanism, where the n plus first agent's role is taken by the seller. Yes. Right?
Okay.
So if I did an n agent optimal mechanism, this is exactly what I would do, where the n plus first agent's role is taken by the seller. But here the advantage of that is that I'm going to always allocate the object to one of the agents in the n plus 1 agent economy. And hence I can use this result to make the claim that the expected revenue of this mechanism is lower than the Vickrey auction for n plus 1 agents.
Sir, does it mean that the expected revenue under Vickrey auction is increasing in N?
That you can derive independent of this, right? So more bidders, more the order statistics values will increase, right? So the expected value of the second highest guy will increase if there are more bidders, right?
Isn't this last bullet point that same argument, or is it something different from that?
No, the last bullet, last point is just the summary of this. So what we have, this mechanism is basically, saying that I can always generate more revenue than the expected revenue of the n agent optimal mechanism, where the n agent optimal mechanism may ask me to set a reserve price, but this n plus 1 agent mechanism basically does better than that. Okay, but I can also improve this n plus 1 agent mechanism by conducting a Vickrey auction, okay, of the n plus 1 agents. Okay, so if I were to write down this n plus 1 agent mechanism, the last bullet has nothing to do with this mechanism that I have just described. This mechanism that I have constructed is just to give you the proof that n plus 1 agent Vickrey is better than n agent optimal mechanism. Okay, because n agent optimal mechanism would require you to know the distribution of the bidders and set a reserve price and so on. But n plus 1 agent Vickrey does not require you any such things. Okay, so what this is saying is that if you're a seller and if you did not know that the distributions of the bidders and so on, but you could hire or acquire an extra bidder. This extra bidder has to be of the same type as the other n bidders, that is the same distribution, same type space, and so on, then you could just conduct this Vickrey auction with this extra bidder, and that will give you more revenue than what you would have got by using this complicated optimal mechanism for any. Is that clear?
But under symmetric case, Vickrey auction with n+1 agent will be the same mechanism that will be with n agents.
But it does not have the reserve price.
So Vickrey auction with n+1 agents here means that without reserve price, zero reserve price.
Okay, sir.
Okay. So the point here is that you could have a prior free auction because there is no reserve price with n+1 agents that dominates the prior heavy optimal mechanism for n agents. Okay. So, right. So Bulow and Klemperer basically, tell the story that, okay, we have n agents and potentially the seller has the option of going to the market and convincing some more bidders to come in. Okay. Well, one possibility is that he just conducts an n agent optimal mechanism, which is a Vickrey auction with a reserve price. But he's not comfortable setting a reserve price because he doesn't know the distribution. So what they are saying is that, well, in that case, he should just go to the market and hire one extra bidder, and do a zero reserve price Vickrey auction. It will do pretty well. Okay, that's what this is saying.
So is there a result that the revenue is somewhat equal as n is very large, asymptotic
The revenue is
result? Equal in the sense that Vickrey auction and optimal mechanism both give the equal revenue as n tends to.
I see. Yes. So intuitively, that would be the case, right? Because with more and more bidders, this square will shrink. Okay, and basically, you would approach the second price auction in that case. Okay, so what
The reserve price will be independent of n.
Which reserve price?
So the WT will be independent of n. So and as n tends to infinity, how the reserve price will go to zero?
So W inverse, in this case, right? Yeah, that's true. So I take that back, right? So what I wanted to say is that if the number of bidders, if I remember correctly, we're increasing the number of bidders, right? So basically the probability or the area of this region as the number of bidders increases as a proportion of the entire Lebesgue measure of the entire type space would reduce. That's what I meant to say. Okay.
Will it reduce to zero?
I have to think, but I think it'll decrease. Maybe the proportion will tend to zero. I think. I have to think. Maybe not. I'm less sure. Yeah, you should think about this.
Sir, in this case, if we increase it to 3 buyers, then it will become basically 5 to the power 3 upon 10 to the power 3. So which is less than 1/4.
Yeah, so it will decrease for sure, but I think I have to do the math. I think it will decrease. I mean, it will converge to zero as n tends to infinity. The ratio, I mean, not the area itself, but the ratio of the areas. Yeah.
So the probability of not selling the object will reduce.
Yeah, it would reduce, exactly. I mean, probability, I mean, the probability of not selling the object in the vis-a-vis the whole type space would reduce, yeah. But there would always be a positive measure of types where the object would be not sold, even for high end, at every end. So the question here is like, if you already have very high end, the probability of not selling the object would anyway be small, because there is a very high chance that somebody will have value more than the reserve price. Okay, so that's basically the intuition, right? Because the reserve price remains the same as you observed, independent of the number of bidders, but now we are increasing the number of bidders. So the probability that somebody has a value more than the reserve price is increasing. So that's basically the intuition.
So can we take away the takeaway from this result? Can it be that as n is very large, it is less costly to conduct a Vickery auction vis-a-vis an auction?
Exactly. Yeah. You can say that. Yeah. So the gains from finding out the exact distribution and setting an exact optimal reserve price will be low if the number of bidders are high. Yeah. Okay. So the other important thing, you should look at the assignment that I have said. The Meyerson toolkit is not about the single object auction only, but it is for many one-dimensional mechanism design problems. Okay, so the toolkit is very, very standard now in mechanism design, and you can use it in any mechanism design problem where the type is just one number. Okay, later in the course I will discuss what happens if the type is multidimensional, but at least in one dimensional problems you can always define a notion of monotonicity, and basically as your type increases, your allocation probability defined appropriately in each of the problems must increase, and that basically defines the F part, and P must be determined by the revenue equivalence expression. And so that's the characterization of IC and IR, and then basically use that to reduce the optimization space to allocation rules, solve the unconstrained problem, and verify that the unconstrained optimal is constrained optimal. So this general approach works in many problems. Some of them I have given that assignment, but beyond that also. And this is something that you should keep in mind, that even though we studied optimal auction design for single object auction, you can also apply it to other kinds of problems. Okay. Okay, so maybe in the next class, so in the notes I have this extension for one buyer and one seller case, which is a monopoly pricing problem. You should read it on your own. I'm not going to cover it in the lectures, but next time what I'm going to tell you is a result that a very stark result that we will get if we allow for correlated types. If the type distribution is no longer independent but correlated. So if we have enough correlation, what I'm going to tell you is that the seller can extract all the surplus from the buyers. So the expected payoff of each of the buyer can be made equal to zero. Okay, if there is enough correlation. So that's the result that we will discuss in the next class. And then we will go to partnership dissolution problem, which is a different kind of problem, but we'll discuss that. Okay?
Sir?
Yeah.
Sir? So as you said that ki in the when it comes to the exposed revenue maximization, then there might be different mechanism for different type profiles that maximizes the revenue at those profiles.
Yeah.
So can we say that when we consider ex ante revenue maximization in which we got the optimal auction, so can optimal auction be interpreted as some kind of combination of all those exposed revenue maximizing mechanism at different type profiles with weights that are some kind of a map of the probability that that type profile will happen.
Okay, so of course the ex ante revenue optimal mechanism basically trades off the gains at some places and losses at some places and chooses the one which maximizes the expectation. Notice that the optimal ex ante revenue optimal mechanism is a deterministic mechanism.
Yes, sir. Yes, sir.
So a deterministic mechanism cannot be written as convex combination of some other mechanism, right? Because it's 1 or 0, so you can never write it as a convex combination of some other mechanism. So it's not in mathematical terms, what we are getting is an extreme point with 0, 1 values. So and it says and it's magical that we get such a solution. Yeah.
Okay, sir.
Okay. Thank you. So see you on Thursday again. Okay.
Okay.